Greetings. Today we're going to learn about the pigeonhole principle. It's a very simple principle. It's quite powerful. The principle says that if there are more than n pigeons in n holes, then some pigeons must share a hole. So let's look at an example. So here is something about Minnesota. So license plate used to be 3 digits followed by 3 letters, and later on they changed it. So let's count the number of different old-style license plate that could be issued. Now this is a review of counting principles. If you have three digits, and then followed by 3 letters, then the 3 digits, there will be 10 cubed different 3-digit combinations. 10 times 10 times 10, and then times 26 times 26 times 26. Make sure you don't add them, you multiply them. And the part B says, what if we have more than that number of cars and we insist on issuing old style license plate only? Let's pretend that we have 10 cubed times 26 cubed plus 1 cars. And then these are the plates. Common sense will tell you that, well, you have too many cars, you cannot issue them different plates. Pigeonhole principle is saying that if we use these as holes, and these are pigeons, we have more pigeons than holes, and there will be multiple pigeons that share the same hole, namely that there will be multiple cars with the same license plate number. So in these, this is part B. In these exercises, what I would like you to do would be to identify which numbers are holes and what are things that are pigeons. And you want to put pigeons into holes, and you want there to be too many pigeons, and then they're squished together. Well, if you need a visual, here is some pigeons sharing the same hole. Right? So this is a cover of a discrete math textbook. So let's look at another example. You should probably pause this video and think about this for a moment before you continue. Number 2, this is a problem from our textbook. Suppose that there are 11 students and they contributed money to a total of $29.54. Was it necessary for some student to give at least $2.70? The question is whether it's necessary. So pause this video and think for a bit and see how you can use pigeonhole principle to help you with that. Did you pause? I'm going to continue. So one idea that you might have is, let's say we have $29.54 collected, and then let's divide that by 11 people, right? And then with 11 people, this equals 2.685454 ... So on average, everybody contributed 2.685454 and so on dollars. That's not what we're asking for, though, because you want to use the pigeonhole principle to say how much would someone need to contribute. The generalized pigeonhole principle allows you to round up. If you round this number up, you would get $3, and that's not exactly what's happening either, because you don't need to round up to a whole dollar amount, but the pigeonhole principle makes you round up to the next integer amount. So you should think of it using integers. So perhaps you have 22,954 pennies, and these are the pigeons. And then you have 11 people, and these are the holes. And if you put the 2,954 pigeons into the 11 holes, then on average, you would need to put that many pigeons into each hole. And now you can round this up. And that would get you, well, it will be this number, but it would be 268.5454, right? So if you round it up, it will be 269. And what this is saying is that there will be someone who contributed at least 269 pennies. Because on average, everybody contributed 268.5454 pennies, it couldn't have been that everybody contributed only 268. I can write this out if you want. So 268 times 11, I'll say plus 6 is equal to 2,954. So here I just want to write it out explicitly to help you think about this situation. If everybody contributed exactly 268 pennies, then we're 6 pennies short from the total amount. Therefore, it couldn't have been that everybody contributed up to 268 pennies because we have some leftover. On the other hand, if everybody contributed 269 pennies, that would be 2959, and that exceeds our number. And so that would be okay. If everybody contributed 269 pennies, then we would have more than enough. Yeah, and then we can ask some of them to take a penny back or so. So it seems like by rounding up, we get, this is the number that we can guarantee someone needs to at least contribute that amount. The original question asked if it wasn't necessary for some student to give at least $2.70, so 270 pennies. Well, this calculation shows no. We could get by without it. Now, please note that this calculation doesn't say someone actually contributed 269 pennies. For all we know, maybe one student contributed 2,954 pennies and everybody else contributed 0 pennies. So it does not say that someone actually contributed 269 pennies. It just says that at least someone needs to contribute at least that amount. So at least one person needs to contribute at least 269 pennies. It might be 3 people who contributed at least 269 pennies. It could be one person who contributed way more than 269 pennies. But it needs to be at least one person, at least this amount. Otherwise, everybody will contribute up to 268 pennies, and that wouldn't be enough. Now that you've seen this average argument, you can go back and look at the previous problem. If you have that plus 1 number of pigeons and you divide that by the number of holes, then on average each hole has 1.0001 or something of that sort pigeons in there. If you divide this slightly bigger number by this slightly smaller number, and then when you round up, the 1.00 something would turn into 2, and so you'll see that there will be at least 2 cars with the same license plate number. Doesn't mean there's exactly 2. Yeah, it could be 7 cars issued with the same license plate number for all we know, but at least 2 cars would have had the same license plate number. If you divide the wrong way, if you try to put holes into pigeons, if you divide, then it will be slightly less than 1, and then when you round up, it will just be 1, and that doesn't really say anything. So make sure you put pigeons into holes, not holes into pigeons. Here's our third and final exercise. I'm throwing 5 darts at a square dartboard, measuring 10 inches on each side, and I didn't miss. Show that there are 2 darts that land within a certain distance away from each other. And then follow-up questions, what if I throw 10 darts? Well, you certainly want to pause this video right now and think about what are your pigeons, what are your holes, and how these numbers come about. So I'll continue, but you should pause and think about this. There are 5 darts. 5 darts. And I'm throwing them at something, and I need holes, and I need pigeons. Looks like I want to have 2 darts that are close to each other. So the darts will be the pigeons. And then I want 1 fewer hole. Then I can use pigeonhole principle and say that 2 darts are in the same hole. because 5 divided by 4, and if you round it up, it will be 2. You don't need this kind of dividing and rounding up when you're just using the vanilla version of pigeonhole principle that says if you have more pigeons than holes, then at least 2 of them are going to be in the same hole. So what are these holes? Let me draw out my dartboard. This is 10 inches on each side, and then we can divide this board into 4 corners, 4 quadrants, let's say. So quadrants. So each quadrant is a 5 by 5 square, and the furthest distance away from 2 points on that square by Pythagorean theorem is 5 square root 2, and that's the number that was given here. So that could have been a hint as well if you have thought about it backwards. So pigeonhole principle says that if I divide the board into 4 quadrants and then I throw 5 darts, then maybe they land like this. Notice I didn't evenly spread them out. Right? All I'm saying, all pigeonhole principle is saying is that at least 2 darts must be in the same quadrant. If you think about it, you have 5 darts, you cannot have all of them in different quadrants. If you have 4 darts, they could spread out, but they could also come together. But we're saying that if they spread out 4 darts, well, then you don't really know if they're in the same quadrant. They could. But with 5 darts, then you're guaranteed to have at least 2 darts in the same quadrant. Maybe all 5 are in the same quadrant. So you cannot say that there's exactly 2 darts in the same quadrant, but you can say there's at least 2 darts in the same quadrant. And in that quadrant, there might be 7 darts, 5 darts, whatever. But those 2 darts, by virtue of being in the same quadrant, they are not too far apart. And so then if you go back to the 10 darts example, then I think you know how to divide that board up. So 10 darts, this was a very tricky question because I thought 5 and 10 would make you think that, that's double. But really, for if you have 10 darts, then you want 9 holes. And so what you would do would be to divide the board into a 3 by 3 grid. And then when you put in 10 darts, then at least 2 of them would be in the same box. See what I did there? You thought I was going to put them all spread out, but then I put them here. That the point is that if you have 9 of them, they could evenly spread out to the 9 boxes. If you have 10, then 2 of them will need to be together, but there could be more of them together. The power of pigeonhole principle is guaranteeing you that there's at least some number of pigeons squished into the same hole. It doesn't say it's exactly that number of pigeons squished into the same hole. So that's it for today, for this video. Bye.